Good morning, everybody, and welcome again to the CIA Maths tutorials. Today we've got Suzanne O'Callaghan to do the tutorial sequences and series. So, okay, Suzanne, I'm going to hand over to you. Good luck with it.
Good morning, everyone. This morning, what we're going to focus on is sequences and series. It's a topic that's related to numbers and patterns. So what we're going to do today is, first of all, I'll introduce the kind of sequences and series that you're going to meet in the Leaving Cert, the notation and the terminology that's surrounding them, the formulae that are all in your tables, which you can access. We're going to look at limit sequences. We're going to look at arithmetic sequences and series. We're going to look at quadratic sequences and geometric sequences. And then we'll do some exam questions. So if you haven't covered the topic before, I've broken it down reasonably simply, but if you want to ask questions, please put a question in the chat and Eamon can interrupt the lecture, and I have no problem at all in explaining something in more detail. The other thing I would say is that don't worry if you struggle with it, with the information I'm giving you, because you will do sequences and series fairly soon in 5th year, and you'll be able to go back over this video and it will help to reinforce what you're learning in school. The other thing I'm going to do as well is I'm going to turn off my video, because I do find that it'll help you to focus on the numbers and the maths rather than being distracted by somebody speaking up in the corner. So I'm going to turn my video off before we go forward. So what are sequences? So as I mentioned previously, they're patterns. So if you look at the first dot there on the left-hand side, you start off with a dot, and the next item in the sequence is a triangle which has 3 dots. The next item in that sequence is a triangle with 6 dots. The next one is 10 dots. So you can see there's a pattern developing here, and the pattern in this one is that they're increasing. So between the first sequence, before the first item and the second item, there's been 2 dots added. Between the second item and the third item, there's been 3 dots added. Between the third and the fourth, there's been 4 dots added. So you see here on the right-hand side, you see some cubes here attached. Starts off with 2, then the next one is 4, the next one is 6. So in that one, you've got 2 added to every single step of the sequence. So that's your pattern. So in the first one, the pattern starts that you add 1, and the next time you add 2, the next time you add 3. And in the right-hand side with the cubes, it's a fixed pattern, continuous pattern where it's just 2 is added to every one of them. So you can see these patterns every day in life. You see some more down here. Excuse me. And the thing is, what we're trying to do is put mathematical terms on them so that you can calculate what the 100th step in the sequence would have in terms of dots or blocks. So it's about putting math formula on this and understanding. So everything in maths is patterns anyway. So once we discover the pattern, we set up a formula for it, and then we use those formula to get solutions to questions. Notation and terminology. A sequence can be referred to as in the items in the sequence can be referred to in terms of U, T, or A. For instance, if a sequence is referred in terms of U, so you have the sequence there, 5, 8, 13. Well, the first one in the sequence is called U1, and in this one it's 5. U2 is 8, U3 is 13. That's the terminology. But UN is classed as what we call the general term. It means that for any term, we don't know what N is. So in a lot of the questions, you will be trying to solve for N. In other words, they might say to you, what sequence will give you 15 dots? So in other words, solve for N. So that's what's called the general term. Now the term before the N term, of course, it would be U of N minus 1. Because if, for instance, the term before U5 is U4, so it's N minus 1. The term after U5 is U6, so it would be U of N plus 1. So that's where that notation comes from. So if you were given a formula, for example, T of n, so now in this case, they're referring to the sequence in terms of T. So T of n, they're saying for any general term, you can solve it by the formula n squared plus 3n. So then what you would do is, for T1, if you wanted to find what's the first item in that sequence, you substitute 1 in for n, and you do that right across the formula. Same for T99. That's the 99th item in the sequence, and we want to know what it is. So you put in 99 squared plus 399, and that gives you the value of the item of the 99th item. So we'll do an example. The first two terms of the sequence u of n is equal to a n plus b are 7 and 11. Find the value of a and the value of b. So they basically said the general term for any term in a particular sequence is u of n is equal to a n plus b. A and b are variables which we need to solve, so they change. But they have helped us in that they've told us that the first two terms of the sequence are 7 and 11. So that means that u of 1 is equal to 7. So we substitute in 1 for n, and we get a times 1 plus b is equal to 7. So a plus b is equal to 7. So that's our first equation that we can use to solve for a and b. The second equation comes from the other given information, which is u2 is equal to 11. Again, we substitute for n is equal to 2. So we have a by 2 plus b is equal to 11. So 2a plus b is equal to 11 is our second equation. Of course, you have two equations in two variables, so you solve them simultaneously. And the output is a is equal to 4, b is equal to 3. So the correct formula for that sequence is u of n is equal to 4n plus 3. You've solved it based on knowing what the two terms are. So in most of the questions, they'll give you information like that. They might give you the first term, they might give you the fifth term, and then you use that information by subbing in values for n to solve to find the actual general equation. So we also have what's called a recursive formula. Using a recursion formula, you can find a term of a sequence from the term or terms that come before it. For instance, all of the sequences are related to one another. So for instance, if I have a sequence 1, 2, 3, 4, and 5, well, the third item in that sequence is related to the one before it and the one after it. The one before it, it's one less. The one after it is one more, is one higher. So a sequence may be described by a recursion formula like this. So for instance, you could be given u of n plus 2 is equal to twice u of n plus 1 plus u of n. So if you look at that formula, what they're saying is, in order to find u of n plus 2, it's based on knowing the term before it and the term before that. So it's based on knowing u of n plus 1 and u of n. And the requirement here is that n is greater than or equal to 1. So the initial terms are u1 is equal to 0 and u2 is equal to 0.5. So this is the information that I've mentioned that they provide to you in order to help you to solve it. So then it follows that for n is equal to 1, u3 is equal to 2 times u2 plus u1, where n is equal to 1. So you substitute 1 into the n. Can you see my arrow moving on the screen? Just a question.
Yeah.
Yeah, okay.
Yeah.
Good, thank you. So in this formula here, we're putting in u of n plus 2. So we're substituting in the value for n as 1. So we come down here, that means u of n plus 1 plus 2 is going to be 3. And that is equal to, according to the formula, 2 times u of 2 plus u of 1. We already know that u of 1 is equal to 0 and u of 2 is equal to 0.5. You substitute them in, so you get twice 0.5 plus 0 is equal to 1. So u of 3 is equal to 1. For n is equal to 2, you substitute it back in again into u of n plus 2, and of course that gives you u of 4 is equal to twice u of 3 plus u of 2. We now have u of 3 because we solved it in the previous line. So, and we also were given u of 2. So we substitute in, we get 2 times 1 plus 0.5 is equal to 2.5. So this is what's called a recursive formula, in that you're using the known values from other elements of the sequence, and other terms of the sequence. To note, the recursion formula could also be written as u of n is equal to twice u of n minus 1 plus n minus 2. So what that means is that this formula up here, the u of n plus 2, if I just wanted to rewrite that formula for u of n, well then I've taken 2 off the subscript here, and instead of n plus 2, I have n. So I have to do the very same with the subscripts here. So instead of n plus 1, take 2 away from that, and I have n minus 1. And instead of n here, take 2 away from that, and I have n minus 2. So this formula here can be rewritten down here as u of n is equal to twice u of n minus 1 plus u of n minus 2. It's the very same formula. You could do that for any n plus 10, but you have to alter the subscripts accordingly. And again, you have to alter the condition, because the condition in this one was for n was greater than 1. So we have to do it for n greater than 3 by adding on the 2. We have to increase that to maintain the condition that we were given. So we'll do example 2 here. Okay, so we're going to do an example. So the diagram below shows the first 4 patterns in a sequence. Each pattern consists of a number of nodes or points joined by line segments. The sequence UN gives the number of nodes in the nth pattern. So you'll see the first element, the first term in that sequence has just 1 dot. The second one has 5 dots. The third one has 12 dots. And the fourth one has 22 dots. So again, there's a pattern developing here. So the question is, it can be shown that u of n can be given by the recursion formula. U of n is equal to u of n minus 1 plus 3n plus 2. So again, u of n is based on knowing u of n minus 1. For n is greater than 2 and u of 1 is equal to 1. So what they've given us is, so u of 1 is equal to 1. And the formula is u of n is equal to u of n minus 1 plus 3 of n minus 2. And what are they asking us for? Use this formula to verify the values of u2, u3, and u4. So we have the first term. We need to find the values for u2, u3, or for, the second term, third, and the fourth. So for n is equal to 2, we have u of 2 minus 1 is equal to, apologies, u of 2 is equal to u of 2 minus 1 plus 3 times 2 minus 2, and that's equal to 4 plus 1 is equal to 5. See up here? That's what we would have expected the answer to be. For n is equal to 3, we have u of 3 is equal to u of 3 minus 1 plus 3 times 3 minus 2. So u of 3 minus 1 is u of 2. And we know that u of 2 is 5. That's going to be 5 plus 9 minus 2 is equal to 12. And again, up here, that's what we would have expected to see. And for n is equal to 4, we have u of 4 is equal to u of 3 plus 3 times 4 minus 2 is equal to 12 plus 12 minus 2 is equal to 22. Again, that's what we would have expected to see. So this is u of 1, this is u of 2, this is u of 3, and this is u of 4. So for here, n is equal to 4, n is equal to 3. Okay? If you have any questions on that, please put them in the chat. Name will direct them to me. So now we'll discuss the limits of a sequence. So the limit of a sequence, u of n, is the number that the terms of the sequence approach as n increases without bound. For instance, as n approaches infinity. Not all sequences have limits. So for example, the terms of a sequence u of n is equal to n over n plus 1, and they're typically a half, 2/3, 3/4, 4/5, 5/6, all the way on. As n gets larger, the terms of the sequence get closer to 1. You can see that. So you started off with a half, and way down in the sequence, you have 99 over 100. It's getting close to 1. So as the sequence progresses, because of the way it's formulated, all the terms are getting closer to 1. So that means that the limit of u of n, and that u of n means any term in that sequence, the limit as n approaches infinity is 1. So the limit of each of them is 1. Or the limit of, as n approaches infinity, of n over n plus 1 is equal to 1. That's how we'd express it. To calculate limits of sequences, there are a couple of special limits that you can make use of. So these are limits that we know and that you can use them in solving your questions. So the first one is that the limit as n approaches infinity of k over n to the power of p is equal to 1, where k is just an element of the real numbers and p is greater than 0. So that means p can't be a negative power. If it was a negative power, the limit of it would not approach 1. So the second one is that the limit as n approaches infinity of r to the power of n is equal to 0. But the requirement there is that r has to be between -1 and 1. What that means is that r is a fraction. So the sequence is fractions to the power of n. And because they're fractions and they have a power, they're to a power of n, the more you multiply a fraction by a fraction, it gets smaller and smaller because you're getting half of a third and half of a quarter and a third of that. It gets smaller and smaller. So what happens is you begin to approach 0. So that's why the limit of any sequence where n is in the power like that, it's 0. And in the first one, the limit where n to the power of p is under the line, your limit of your sequence there is 1. So the procedure for calculating limits of sequences. Divide above and below the dominant term. So for instance, you'd have a sequence given there that would be 5n squared plus 4 over 2n squared minus n plus 6. And you might be asked to find the limit of that. So the method is, the first thing you do is you divide above and below the line by the dominant term. Okay, so I'll actually do it out for you. So we have an example here. So evaluate the limit as n approaches infinity of n squared minus 4n plus 5 all over 3n squared plus 7. So the solution there would be to divide above and below by the highest power of n. So we have the limit as n approaches infinity of n squared minus 4n plus 5 all over 3n squared plus 7 is equal to the limit as n approaches infinity of n squared minus 4n plus 5 all over n, and that's all over 3n squared plus 7 divided by n. So you're dividing above and below the line by n. So that's equal to the limit as n approaches infinity of 1, sorry, I'm just dividing by n squared. Take there, n squared, highest power. So n squared, first one there, n squared divided by n squared is 1, minus 4n divided by n squared is 4 over n, plus 5 over n squared. And below the line, we have 3n squared divided by n squared is 3, plus 7 over n squared. So now let's look at each of them and assess their limits. So the limit of 1 is going to be 1, because the limit of any number that's an actual constant, it doesn't change. No matter what infinity is, no matter what n is, 1 will always be 1. Now, for this one, minus 4 over n, as n approaches infinity, you could eventually end up with 4 over infinity. Now, if you look at normal fractions, 1 over 2, 1 over 1,000, which one is the smallest? The one that's the smallest is the one that has the biggest number under the line. So as infinity, as that number, the denominator gets huge, this number approaches 0. It becomes, the limit of it is 0. It gets so small, it becomes such a tiny fraction, it approaches 0. So it approaches 0. The same for 5n squared, 5 over infinity squared, again, that approaches 0. The limit at the bottom of the line of 3 is 3, it's never going to change. And again, we have 7 over n squared, that's 7 over infinity squared, that's the limit of it. That's definitely going to approach 0. So our answer is 1 minus 0 plus 0 all over 3 plus 0 is equal to 1 over 3. So the limit as n approaches infinity of n squared minus 4n plus 5 all over 3n squared plus 7 is equal to a third. In other words, if n was infinity, that's the limit that it would approach. It wouldn't go beyond that. So now the limit of a sequence given by a recursion formula. Sometimes it has a limit. If it does, the recursion formula can be used to find that limit. And we have a method for finding the limit is based on the fact that if the limit as n approaches infinity of u of n is equal to u, well then all other terms have the same limit, because u of n is a general representation for every term in your sequence. So if you've been told that the limit as n approaches infinity of u of n is u, well then every other term in the sequence has the same limit. For instance, the limit as n approaches infinity of u of n plus 1, it too will be equal to u. We'll do an example again to demonstrate that. So we have a recursive sequence here. For a sequence u, u1 is equal to 1, and u of n plus 1 is equal to u of n squared plus 2 all over u of n. Again, the formula is recursive. Why? Because finding the value of u of n plus 1 depends on you knowing the value of u of n. And that's for n greater than or equal to 1. So the first part is if the limit as n approaches infinity of u of n is 1, find the value of u greater than 0. In other words, find the value of any positive u. So we know if the limit as n approaches infinity of u of n is equal to u, then it follows that the limit as n approaches infinity of u of n plus 1 also is equal to u. Again, like we said on the slide, if any general term in that sequence, the limit of it is u, well then the limit of u of n plus 1 is u. So we're given in the question u of n plus 1 is equal to u of n squared plus 2 all over twice u of n. So what we do is, if we get the limit of both sides, which we know the limit of both sides, we have the limit as n approaches infinity of u of n plus 1, that's coming from here, get the limit of that, is equal to the limit as n approaches infinity of u of n squared plus 2 all over twice u of n. We know that the limit of u of n plus 1 is u, and that's equal to the limit of u of n squared plus 2 all over twice u of n, twice the limit of u of n. So here we're evaluating the limits on this side of the equation here. So the limit of u of n squared, the limit of u of n we know is u. So that's going to be u squared plus 2 all over twice the limit of u of n. And we know the limit of u of n, as previously given, is u. That's over u. So the answer is u squared plus 2 all over twice u. So that's equal to u. So coming down from here, we have u equals u squared plus 2 all over twice u. That's twice u squared. We cross multiply. Is equal to u squared plus 2. U squared is equal to 2. So u is equal to square root of 2. So that's your value of u is equal to the square root of 2. So we go back to our question here. Find the value of u greater than 0. In other words, positive u. And we found that as square root of 2. So the next part of the question is use u4, correct to 4 decimal places to obtain an approximate value of square root of 2. Use U4 to find an approximate value of square root of 2. So what do we know? We know that U1 is equal to 1. U2 is equal to, based on our formula, 1 squared plus 2 all over twice U is equal to 3 over 2. U3 is equal to 3 over 2 squared plus 2 all over twice 3 over 2, because we're using this in our recursive formula. Let me write out our recursive formula again, just to remind you. U of n plus 1 is equal to U of n squared plus 2 all over twice U of n. Okay? And that gives us equal to 17 over 12, and that's equal to 1.4167. Now that's getting close to the value for the square root of 2. But they did say use U4, and we couldn't use U4 because all we had was U1. So we had to work our way down, solve for U2, solve for U3, and now we can solve for U4 because we have the value of U3. So U4 is going to be 17 over 12, which is U3 squared plus 2 all over 2 times 17 over 12. That's equal to 577 all over 408. And that's equal to 1.4142. That's what we wanted. That's equal to square root of 2. So they instructed us to use U4 to find the approximate value of U2. The only value that we knew was U1, but that helped us to solve for U2. Then having the value of U2 helped us to solve for U3, and having the value of U3 helped us to solve for U4. And by evaluating U4, we got an approximate value for U2, for the square root of 2. Because we did find that all the U's are equal to the square root of 2. That helped us to find the approximate value. So next, we're going to have a look at arithmetic sequences. These are the ones I showed you diagrams for in the beginning. They're basically ones that can be constructed by adding or subtracting a term to the previous term and adding it on to one term to get the next term. So the definition is an arithmetic sequence is a sequence in which every term after the first can be constructed from the previous term by adding on or subtracting the same fixed constant. So that's important. It's the same fixed constant. An example here is 3, 7, 12, 15. The same fixed constant here is 2. So 2 is added on to each term. So the identification is that there are constant differences. Again, here, the terms 2.7, 4.1, 5.5, the first difference. In other words, if you subtract each term from the term after it, you'll get 1.4. The general definition, in order to prove that a sequence is arithmetic or to understand, to check if it's arithmetic, is take one term from the other. Take the previous term from the following term, and you should get a constant. So the definition is t of n minus t of n minus 1 is equal to a constant for all n is greater than or equal to 1. So you see there, all n is greater than or equal to 1. Why is that? Sure, n has to be greater than 1 because there's no such thing as t0. There's no such thing as a 0 term. The very first term in every sequence is going to be t1, which means n always has to be 1 or greater than that. So the arithmetic sequence formula must be linear and of the form p of n is equal to p times n plus q, where p and q are constants. So we'll do an example. So prove that the sequence t of n is equal to 5n plus 2 is arithmetic, and then prove that the sequence u of n is equal to n squared plus 1 is not arithmetic. So if t of n is equal to 5n plus 2, t of 1, or t of n minus 1, is equal to 5 times n minus 1 plus 2. See that wherever there's an n and you replace it with n minus 1, you've got to replace it in the formula as well. So that's going to be equal to 5n minus 3. So get the difference between them. Between Tn and t of n minus 1. It should generate a constant. So we have t of n minus t of n minus 1 is equal to 5n plus 2 minus 5n minus 3. What's that equal to? 5n plus 2 minus 5n plus 3 equals, so 5n minus 5n is 0, 2 plus 3 is equal to 5. There's your constant. So we know it is an arithmetic sequence. So we have in 2, t of n is equal to n squared plus 1. The t of n minus 1 is equal to n minus 1 squared plus 1. That's equal to n squared plus n squared minus 2n plus 1 plus 1. That's equal to n squared plus 2n plus 2. So we do again tn minus t of n minus 1. So that's equal to n squared plus 1 minus n squared plus 2n minus n squared. That's minus 2n minus 2. The n squared minus n squared is gone. And we have 1 minus 2 is minus 1. And we have minus 2n. So that's not constant because n varies. The value, the difference between them is minus 1 minus 2n, and n varies. So it's not constant. You don't have the same number, which means it's not an arithmetic sequence. It is still a sequence, but it's not arithmetic. So the general terms for the arithmetic sequence and series. The first term is always called A. So A is the first term, and that's the equivalent of T1 or U1 or any other letter you want to use. The common difference is the constant difference between them is called D, and that's equal to T2 minus T1. And the formula for an arithmetic sequence is T of n is equal to A plus n minus 1D. That's your standard formula for an arithmetic sequence. So you need to understand those three terms for working with arithmetic sequences. So we have a question here on arithmetic sequence. In an arithmetic sequence, the fourth term is 15 and the 11th term is 3 times the third term. Express t of n in terms of n, and then find the value of n if t of n is equal to 852. Okay, so we're given, always write down what you're given. So we're given that t of 4 is equal to 15. And we also know that t of 11 is equal to, what did they say? The 11th term is 3 times the third term. So it's 3 times t3. So this is all that we're given. But we also know that t of n is equal to a plus n minus 1 d. That's our general term. General equation of that. So if t of 4 is equal to 15, that implies that a plus 3d is equal to 15. Based on this formula here, we substitute for t of 4 that n minus 1 is 3. So we generated the first equation in 2 variables that will help us to solve. So we have t of 11 is equal to 3t times 3, which is equal to a plus 10d based on the t of n formula. And we know that t of 3 has to be equal to a plus 2d. So up here to this side. So we'll move up here to the side. So now we have 3 times t3 is equal to 3 times a plus 2d, which is equal to 3a plus 6d. But we know that t11 is equal to 3t3, and it's also equal to a plus 10d. So equate the two of them. A plus 10d is equal to 3a plus 60. Solve that, and we get 2a minus 4d is equal to 0. So a is equal to, or a minus 2d is equal to 0. And that generates our second equation. We now have a plus 3d is equal to 5. We have a minus 2d is equal to 0. We solve that, minus plus, they go, and we get 5d is equal to 5d is equal to 1. Okay. Values are wrong here somewhere. A plus 3d, that's 15. Mistake there, did I? Yes, 3t4 is equal to 15. Mistake there. Mistake there. T4 is equal to 15. That's where that came from. That's 15. 3. And then I solved it. Find a, and we get a is equal to 6. So T of n then is equal to, our general term is equal to A plus n minus 1d. We substitute in the values for A and D. So we get T of n is equal to 6 times n minus 1 by 3. That's equal to 3n plus 3 for T of n. So that's your formula. We'll do the last part of the question and then we'll take a break. So just to reiterate, we were given two terms, T4 and T11, and we use the information we have on the value of them, which is 15 and 3. And we also use the information we have based on the general Tn formula. And we use those to generate two equations in two variables, that is A and D, that we can then simultaneously equate and solve for the values of A and D. And that gives us Tn is equal to 3n plus 3. So the next part of the question is, find the value of n if Tn is equal to 852. So find the value of n if T of n is equal to 852. So what are they asking? Find the value of n. In other words, they're asking which term is equal to 852. So that's straightforward enough. We know that Tn is equal to 3n plus 3. They've told us that it's equal to 852. So now we try and solve this equation in one variable. So we have 3n is equal to 849, and n is equal to, here, 283. So the 283rd term has a value of 852. Hello and welcome back. So in the last question, we used the general terms of A, D, and Tn in order to solve a question. And now we're going to move on to another formula that you will add to that, which is it's a formula for the sum of terms. So S of n is equal to T1 plus T2 plus T3 all the way up to Tn. In other words, you're adding up all the terms and you get a sum. And that's called S of n. And the formula for it is S of n is equal to n over 2 multiplied by 2a plus n minus 1d. So we'll do two examples, 7 and 8, where the sum formula is used. So example 7, find a formula for the sum to n terms of the arithmetic sequence. In other words, instead of us using the sum formula, they're asking us to find it. So our arithmetic sequence are 2 plus 8 plus 14. So first things we usually need to find are A and D. So what's A? A is the first term, so it's 2. A is always the first term. D is the common difference, because we're talking about an arithmetic sequence. So the difference between them is between 2 and 8 is 6. Between 8 and 14 is 6. So there we go, our common difference is 6. The formula for S of n is equal to n over 2 times 2a plus n minus 1d, which is equal to n over 2 is equal to 4 plus n minus 1 times 6. Oh, wait a minute. Apologies. equals in the wrong place, is equal to n over 2. That is equal to n over 2 into 6n minus 2, which is equal to 3n squared minus n. So our S of n is equal to 3n squared minus n. That's what we're looking for. That was a simple substitution. The next part, use this formula to evaluate 116 plus 122 all the way up to 266. So effectively what they've done here, it's a little bit tricky because the sum of n, which is the sum formula, adds up all of the terms from T1 all the way up to the last term, which is Tn. That's how the formula works. You have to have the first term all the way up to the last term. But here in this formula, what they have done is they've picked a chunk out of the sequence. Obviously, at the start of the sequence is 2 plus 8 plus 14, ... But they're only asking you to evaluate this much, the sum of this much. But this S of n formula will give you the value of, because that's T1 and T6 is Tn. So that is the S of 1. S of n, apologies, S of n will evaluate everything from T1 to Tn all added together. But you only want to know what's the value from this term, which we don't know what it is, all the way up to the last term, and we don't know what the last term is either. In other words, what number they are. So what we need to do is we need to find the value of S of n and subtract from it the sum of these terms here. So it would be S of n minus sum. Okay? So how do we go about doing that? We now first need to find out what's the term before this. We need to work out the sum to here. From term 1 up to term here, but we don't know. But based on the common difference, we know that there is 6 between them all. So that means that 110 is the last term here in this sequence. But what is the term? What is n for that term? So how do we find it? And we also need to know for 266, what is n in this as well, so that we can calculate S of n. We don't know what n is for each of those terms. So T of n we know is a plus n minus 1d. And we know that a is 2, so we have 2 plus n minus 1, 6 is equal to T of n. But we do know that the T of n for the 110, we know that that is equal to 110. We know that the value of it is 110, so that's equal to 2 plus 6n minus 6. Here, this is just the evaluation of it. Okay, so 6n is equal to 114 and n is equal to 19. Which means that this 110 here is term T19. That's what we were trying to solve. And we do the same for 266. We don't know what n is. So we know that 266 is equal to 6n minus 4. Remember, the general term is 6n minus 4. So 6n is equal to 270. N is equal to 45. So now we know that the 266 is term 45. So our solution is going to be to get the sum of all the terms up to 45 minus the sum of all the terms up to 19. And that will give us the value of this part here of the sequence. Okay. Our formula for S of n is 3n squared minus n. We solved that already. So our S of 45 is equal to 3 times 45 squared minus 45. S of 19 is equal to 3 times 19 squared minus 19. And that is equal to 45 times 134 minus this one is 19 times 56. And that is 4966. So the sum of 116 plus dot up to plus 266. Sum of those is equal to 4966. But they didn't give you a straightforward sum of terms question there. Do another example based on that. Excuse me. So the 15th term of an arithmetic sequence is 57, and the sum of the first 21 terms is 861. Find the sum of the first 30 terms. So they've given us that T15 is equal to 57, and they've also given us that S21, the sum of 21 terms, is 861, and they want us to find the sum of the first 30 terms. So T then is equal to A plus n minus 1 D, and the S of n is equal to n over 2 times 2A plus n minus 1 D. There are terms of general formula. So T15 is going to be equal to A plus 14D, and we know that's equal to 57. Straight away, that's our first equation in two variables. S of 21 is equal to 21 over 2 times 2A plus 20D, and that's equal to 861. Tell you that up a bit more. So that is 21A plus 2ND equals 861. Second equation. And then we solve simultaneously. I won't spend the time doing that now. Find A and D. Once you find A and D, you then substitute in your, let's see. No. So you then substitute in 30 into your formula for 30 over 2 into 2A plus 29D. And that gives you your answer. So the key at the beginning of the question is take what you're given, take the value of the numbers, which are 861, 57, and equate them to the formula that you've been given, the standard formula for an arithmetic sequence. And that creates your two equations in two variables that you can solve simultaneously. Now we'll go on to our quadratic sequences. We've already discussed arithmetic sequences, which are sequences where the difference between the terms is a constant difference. Now, the sequence is quadratic if the first differences between successive terms are not constant. In other words, you get a different number every time you subtract one term from another. However, the second differences are constant. In other words, when you get the first differences, you subtract the first differences from each other, and that's what's called the second differences. When they are constant, you know you have a quadratic sequence. So you have the formula for a quadratic sequence. It's T of n is equal to an squared plus bn plus c. Again, a, b, and c are constants. But the thing that's really important to remember is that a is always equal to half the second difference. You can get the second difference by subtracting the first differences. You get a constant second difference, but half of that is a for that formula. That's the key to solving those questions. So we have an example here. The sequence is 4, 6, 10, 16, and the pattern is continued. Verify that the sequence is not arithmetic. So let's write them up. So we have 4, 6, 10, 16, and so forth. Let's get the differences between them. 4 from 6 is 2. 6 from 10 is 4. 10 from 16 is 6. So not constant. So it's definitely not arithmetic. 2 from 4 is 2. 4 from 6 is 2. So those were the first differences, and these are the second differences. And it's constant. And that implies it's a quadratic sequence. And that also tells us that A is equal to half second difference, which is equal to 1. Straight away, we've that information garnered. So you have verified that the sequence is not arithmetic. Show that the sequence is quadratic, which we have now done. So we've done part 1 and 2. Part 1 and part 2. Both done. If the general term of the sequence can be written as T of n is equal to an squared plus bn plus c, find the values of a, b, and c. In other words, they've given us the first 4 terms of the sequence, and they want us to write out the general formula for the term. So we have Tn is equal to an squared plus bn plus c. And a, we know, is equal to a half. So T1, first term, which we already know, is, based on this formula above here, is going to be 1 plus b plus c, and we know it's equal to 4. So we have b plus c is equal to 3. Equation there. T2 is equal to 4 plus 2b plus c, and what do we know T2 is equal to? It's equal to 6. So that gives us 2b plus c is equal to 2. Another equation there in two variables. B plus C is equal to 3. 2B plus C is equal to 2. Solve them, and we get B is equal to -1 and C is equal to 4. So Tn is now equal to n squared minus n plus 4. So you should see a pattern developing here in terms of how to deal with sequence questions. They will give you the term and you use the value of that term and the general formula in order to solve for n, t of n, or s of n. So now we move on to geometric sequences. So the definition is a geometric sequence is a sequence in which every term after the first term can be constructed from the previous term by multiplying or dividing by the same fixed constant. If you recall in arithmetic, we add or subtract to the previous term. In geometric sequences, we multiply or divide by, again, a fixed constant. We have an example here. We have 2, 6, 18, 54. What's the fixed constant there? It's 3, and each one is multiplied by 3. So 2 multiplied by 3 gives you 6. 3 6s will give you 18. 3 18s will give you 54. So there is a constant ratio between successive terms of the sequence. And how do you know? You just divide one by the other. If you divided 18 by 6, you get 3. If you divided 54 by 18, you get 3. So in general terms, it looks like t of n over t of n minus 1 is equal to a constant. And that's for all n greater than or equal to 2. A sequence is geometric if it can be written in this form. T of n is equal to p times q to the power of n, where p and q are constants. So that's how a geometric sequence is written. The general terms of a geometric sequence are that the first term is always a again, but the common ratio this time is or, not d. You're used to using d in the arithmetic, whereas in the geometric it's or. It's a common ratio because you're dividing one term by the other, and it's a ratio. The formula is of the format Tn is equal to a times or to the power of n minus 1. Again, you can see there, in order to solve for t of n, to find the nth term, you need to use n minus 1 in the formula. So we'll do some examples. So in this example, we have a question that says, show that the sequence given by this formula, t of n is equal to 3 times 2 to the power of n minus 1 is geometric. For this sequence, find the first term and the common ratio. So how do we know if a sequence is geometric? Well, typically, we would divide one by the other. So we have t of n is the general formula, and that's 3 times 2 to the power of n minus 1. And t of n minus 1, which is the term before it, is going to be 3 times 2 to the power of n minus 1 minus 1. So it's going to be n minus 2. So we have t of n all over t of n minus 1 should generate a common ratio, which is equal to 3 times 2 to the power of n minus 1 all over 3 times 2 to the power of n minus 2. 3's cancel, and we're left with 2 to the power of n minus 1 divided by 2 to the power of n minus 2. What do we do? Go back to your indices. If you have a to the power of x divided by a to the power of y, the answer is a to the power of x minus y. So we have 2 to the power of n minus 1 minus n minus 2, which is equal to 2 to the power of n minus 1 minus n plus 2 is equal to 2 to the power of the n's are gone, and we have minus 1 plus 2. So we have 1 is equal to 2. So R is equal to 2. That's answer to the first part. For this sequence, find the first term and the common ratio. So they're looking for the first term. So T of 1 is also the first term. We call it A, but we also call it T of 1. And that's going to be 3 to the power of 2 to the power of 1 minus 1, which is 3 to the power of 2 to the power of 0. What's anything to the power of 0? X to the power of 0 is always 1. So that's equal to 3. And R is equal to 2. We've solved it already. So you found your first term A is 3. And your R is 2. Next example, a geometric sequence has a third term of 48 and an eighth term of 3, 7, 3, 2, 4, 8. Find the value of the sixth term. So it's a geometric sequence. So we know T of n is equal to A R to the power of n minus 1. And T of 3 is equal to 48. And T of 8 is equal to 3, 7, 3, 2, 4, 8. So T of 3 is also equal to A R squared. And we know that's equal to 48. That's our first. And we know that T of 8 is equal to A R to the power of 7. And that's equal to 3, 7, 3, 2, 4, 8. Second equation. And if you divide one by the other, you divide A R to the power of 7 divided by A R squared. It'll help us to solve this. 3, 7, 3, 2, 4, 8. And I'm dividing them by each other for no other reason other than to solve them. So if you divide those two, you have to divide these two. Okay? And that gives us AR to the power of 7 divided by AR, so the A's cancel. R to the power of 7 divided by R squared is R to the power of 5. And that's equal to 7, 7, 7, 6. And R is equal to 6. So find the value of the sixth term. So we have R, we haven't found A yet. So if AR squared is equal to 48, then we have A by 6 squared is equal to 48. So solve that and we get A is equal to 4 over 3. So now we have A and we have R, and we need those to solve for T6. So the next part is to find the value of the sixth term. So T of 6 is equal to A R to the power of 5, and that's equal to 4 over 3 by 6 to the power of 5, and that's equal to 1036. That's the sixth. That's the value of the sixth term. So the sum of terms is similar to the arithmetic sequence. The geometric sequence also has a formula for the sum of terms, and it is S of n is equal to A times 1 minus R to the power of n minus 1 all over 1 minus R, where R cannot be equal to 1. So you will find all these, you will find the T of n and the S of n formulae in your tables for both arithmetic and geometric sequences. So we have this example, find the formula for S of n for the geometric series. Oh yeah, another thing is they're calling it series as opposed to sequence. The difference being that if you have 1, 2, 3, 4, 5, with a comma between all of them, it's a sequence. If you have 1 + 2 + 3 + 4 + 5, it's a series. And when you're getting the S of n of something, of terms of sequences, well, then you're getting a series because it's the sum of the series because they're all added together. So in this series, A is equal to a half. What's R? R is equal to T of n divided by T of n minus 1. And that's equal to 3 over 2 divided by a half. And that's equal to 3. So our S of n is equal to A times 1 minus R to the power of n all over 1 minus R. We substitute in the values we have and we get a half into 1 minus 3 to the power of n all over 1 minus 3. So S of n is equal to 1 minus 3 to the power of n all over minus 4, which is equal to 3 to the power of n minus 1 all over 4. So that's your formula for S of n. Find the value of n if S of n is equal to 1640. So they're not asking you to find the sum, they're giving you the value that's the sum, and they're saying find what term comes to that sum. So they're giving you S of n is equal to 1640. So then you just say, okay, well, 3 to the power of n minus 1 over 4 is equal to 1640. 3 to the power of n minus 1 is equal to 6561. Here, to solve this, you need to go to your logs. So you get the log of both sides. So you get n is equal to the log to the base 3 of 6561, and that's equal to 8, which means that S of 8 is equal to 1640. What does that mean? That the 8th term, when you add up all the terms, from 1 to 8, you get 1640. So in that question, you were looking for n. You have to solve for n. Now we go to infinite geometric sequences. So it's of the form, a geometric sequence is of the form a plus ar plus ar squared plus ar cubed. Because remember, we're multiplying each successive term by r. So of course, the first one will be a, the second one multiplied by r will be ar, the next one multiplied by r again, because that's your common ratio. So an infinite geometric series has no last term. Some have a finite sum in that they're convergent. Now, what does convergent mean? So it means the sum to infinity converges to a point, to a finite sum. I'm going to show you a visual example. So this is an example of a geometric convergent series. Look at the purple square. So it's converging all the time. So the first term in the sequence is a half by a half. Okay, so it's a quarter. Then this next term is a quarter by a quarter. So it's reducing. If you look at it, the boxes are reducing by a half. This is a typical converging series. And it gets smaller and smaller and smaller, but it converges to a finite sum, as in you add up all of those and you get a finite sum. It's because it ends at a finest point where you're going from this big purple square all the way down to the corner there. You're adding up all those successive terms and you will get a finite sum at the end of it because it gets so minuscule at the end. You'll be classing the very, very last terms as 0. But if you look now at the yellow boxes, that could give you an example of a divergent series diverging in the direction from the top right-hand corner out. The boxes are getting bigger and bigger and bigger and bigger and bigger. And they'll eventually go to the size of infinity. So you can't ever add them all up and come to a finite value because it'll be infinite. So that's an example of a divergent series, the yellow boxes getting bigger and bigger and bigger, okay? So some have a finite sum and they're convergent and it's sum to infinity, and it's only if r is between -1 and 1. Why is that? If r is between -1 and 1, it means it's a fraction. And by multiplying something by a fraction, you're reducing each successive term. So they reach like the box, like the purple box. So it reaches down to the tiniest amount at the end. It gets so small at the end, the last terms are equivalent to 0. So you can add them all up and have a finite sum. It works when r is a fraction, okay? In other words, it's converging down to a small point. If r is multiplying by 2 and 3 and 4, that's an example of a divergent series, because you're multiplying by a whole number, and it means that the terms are getting bigger and bigger and bigger, and as n approaches infinity, well, of course, the sum becomes infinite and you can't put a sum on it. So if r is less than or equal to -1, or r is greater than 1, there is no finite sum, it's divergent. So that's exactly what I was saying. If it's greater than or less than -1, in other words, if it's a whole number, it's a divergent series, because the sizes of the terms get too big. But if r is between -1 and 1, well, then it has to be a fraction. And if it's a fraction, it does reduce down and it does converge. The sum to infinity is s of infinity is equal to a over 1 minus r. That's only if r is between -1 and 1. We're going to do an example on that. The sum of the first two terms of a geometric series is 9, and the sum to infinity of the series is 12. If the series has a positive common ratio r, find the value of r at the fourth term of the series. So what have they given us? They have given us that s of 2, sum of the first two terms, is 9, and the sum to infinity is 12, or has to be greater than 0 because it has to be positive, and find T4. So T1 is equal to A. We know that. T2, it follows, is AR. And we know that T1 plus T2 is equal to 9. So A plus AR is equal to 9. Sum to infinity is 12, but it's also equal to A over 1 minus R, and that's equal to 12. So A is equal to, what did I write there? 1 minus R, apologies. So A is equal to 12 times 1 minus R. Again, another equation here. First equation, second equation. But in this case, we're going to do substitution. We're going to substitute S of infinity into. So we have A times 1 plus R is equal to 9. So that's S of 2. We're going to substitute in S to infinity. So because we know what A is down here. Here, based on S to infinity, we were able to generate a value for A. So we're going to substitute for that back in here. So now we're going to use that and say 12 times 1 minus R by 1 plus R is equal to 9. Now we have an equation in one variable that we can solve. So 1 minus R by 1 plus R is typical sum of product of two squares. So you have 1 minus R squared. Remember, A minus B by A plus B is equal to A squared minus B squared. Okay, is equal to 9. 1 minus r squared is equal to 9 over 12. We have r squared is equal to 3 over 12, which is equal to a quarter. So r is equal to a half, and r is greater than 0. All right, we just do that by substitution. The last part of the question is find the value of r, which we have done, and the fourth term of the series. So we know that a is equal to 12 times 1 minus r. R is equal to half, so we solve it by getting r is equal to 12 times 1 minus a half. So a is equal to 6. So T4 is equal to a r cubed is equal to 6 times a half, or 3 is equal to 3 quarters. So T4 is equal to 3 over 4. Now, recurring decimals. A recurring decimal is a decimal number which contains a group of digits repeated to infinity. You've seen them before. You've got something like 3.25.17 dot is equal to 3.25175. So the dot, for any of you that aren't familiar with it, means that the 5 is repeated, and the dot over the 7 means that the 7 is repeated. So because it's between, so the dot is 5 from 5 to 7, it means that the 517 is repeated all the way. So every recurring decimal can be written as a rational number, as in p over q. It's an element, it's an integer, where q is not equal to 0. Q can never be equal to 0 if it's under the line, otherwise your number is undefined. So an infinite geometric series can be used to write any recurring decimal in a rational form. Believe it or not, that there is a series there in that number, and we're going to break it up to show you how you can solve and reduce that number to a fraction. So we have, by forming an infinite geometric series, write 4.25 dot is equal to 4.255, and write it in the form of p over q. That's what they want to see. So 4.25 dot is equal to 4.2555. We're going to break that down now and see what that looks like. So 4, this number can be written as 4 plus, what's the value of 2? It's 2/10. 4 plus 2/10 plus, now each of those, so that's 4, that's 2/10, that's 5/100. So that's plus 1 over, or that's plus 5 over 100, plus 5 over 1,000, plus 5 over 10,000, plus 5 over 100,000, and so forth. Okay, so that number 4.25 can be written like that as well. In other words, if I had number 5, it can be written as 2 plus 2 plus 1 plus 0.5 plus 0.5. That's what we're doing. And what we've done is we've established, we've shown that there's a series there from that point onwards where the 5 repeats. But it's a series where the first term is a, is 5 over 100. And the recurring term, the common ratio is what? They're all multiplied by 1 over 10. Okay, so an r is a fraction in this case. So as r is greater than or equal to -1 and less than 1, it's in between 1 and -1. It's a fraction of the form p of q equal to 1 over 10. Because it's in that form, we can use s to infinity formula of A over 1 minus R. Remember, the requirement for that to use that formula was that R was a fraction. Okay. So 4.25 then can be written again as 42 over 10. So we could write 4 as 40 over 10 also. And 40 over 10 plus 2 over 10 is 42 over 10 plus the sum to infinity, which is equal to 42 over 10 plus A over 1 minus R, which is equal to 42 over 10 plus, that's our A, 5 over 100 divided by 1 minus R is 1/10. Okay, that's equal to 21 over 5 plus 5 over 90, which is equal to 383 over 90. So the sum to infinity is equal to 383 over 90. But the only reason that we were allowed to use that formula was because R was a fraction. So this is our last question, and I'd encourage any of you, if you want to put questions into the chat that I can address and go back on anything in the slides that you need me to go over again, or if you need another question, if you need me to go over another example, I can do that and explain it again. So there's no problem with that. So in an arithmetic sequence, the sixth term, I'm just going back and pick the general exam question here. So in an arithmetic sequence, the sixth term is half the fourth term, and the third term is 15. Find the first term and the common difference. So it's a bit of a recap. So the sixth term, they've told us, is T6 is equal to half the fourth term, T4, and T3 is equal to 15. So T6 is also equal to A plus 5D, based on our formula for arithmetic sequences, probably forgotten it by now, which is A plus N minus 1D. And T4 is equal to A plus 3D, and T3 is equal to A plus 2D. But we know that T3 is equal to 15. So that's the first equation that we can create. And we know that T6 is equal to half of T4, which is half of A plus 3D. This implies that A plus 5D, which we know from here, is also equal to half of, up here, A plus 3D, because we have two ways of expressing T6. We can express it in terms of T4, and we can express it in terms of T6. We equate both of those formulas, and we get 2A plus 10D is equal to A plus 3D, and we get A plus 7D is equal to 0. The other equation. So we have A plus 2D, A plus 7D, that's equal to 15, this is equal to 0. subtract. They go, we get minus 5d is equal to 15. But d is equal to minus 3. And if d is equal to minus 3, we take a plus 2d is equal to 15. That's one of our equations. So a is equal to 15 minus 2d. That means a is equal to 15 minus 2 by minus 3. And that's equal to 21. So a is equal to 21. So we solve for a is equal to 21 and b minus 3. How many terms are needed to give a sum that is less than 65? So this would be a typical exam question. Let's go up here. So how many terms are needed to give a sum that is less than 65? But the sum of n is less than 65. In other words, find n. Okay. So we start off with our S of n formula, which is n over 2 times 2a plus n minus 1 d is less than 65. D is equal to minus 3. A is equal to 21. So we have n over 2 times 2 into 21 plus n minus 1 by minus 3 is less than 5. Brings us to n over 2 into 42 minus 3n plus 3 less than 65. N into 45 minus 3n is less than 130. So we have 45n minus 3 n squared less than 130. So we have 45n minus, so we can rewrite that a bit by moving things over and back. We get 3n squared minus 45n minus 130. 0 for the purposes of solving it. Solve for x, solve for n. And you have to use n is equal to minus b plus or minus square root of b squared minus 4ac all over 2a, another formula that's in your tables. And when we solve that, we get n is equal to 11.1 and we get n is equal to 3.9. Okay, so don't forget that we had an inequality here. So n is greater than 11.1 or n is less than 3.9. So we can't use 11.1 as a term. There's no such thing as term 11.1. So the term is either term 11 or term 12. And in this case, the term, or sorry, that's 3.9. Okay, so the term is either 3 or it's term 4. Remember, they're asking the question, what's the term, how many terms to give the S of n less than 65? You're probably looking at it and wondering, well, how can, if you go up to 11, if you go over 11 terms, the sum of it isn't 65, it's over 65. If you go less than 3 terms, the sum is, it's because the terms, it's a geometric, or it's an arithmetic sequence, it's adding and subtracting. And the terms, the sums vary at different stages. So they want to know at what terms at what point in the sequence, if you add up all those terms leading up to that point, does the sum of it stay under 65? So in this case, we must have 3 terms or less to give us 65, or we have to be greater than 11. So if we're greater than 11.1, that means it has to be term 12. If we're less than term 3.9, well, then it has to be term 3. Okay, so the answer, the solution to it is, you just probably need to sit and get your head around it. The solution is up to 3 terms. You add up the first 3 terms, the sum, 3 terms, is less than 65. But over 12 terms, is less than 65 also. But they're your solutions to the question. You've solved for n and you found it's either 11.1 or 3.9. If it's 11.1, it has to be either 11 or 12. So it can't be greater than 11.1. So you have to go up to the next available term, the next whole term. So greater than T12, the sum up to T12 and over will give you a value that's less than 65. And if you add up the first 3 terms only, you get a value of S of n less than 65. So there are your 2 values. And the question is, you're probably thinking, how do you know which one that it's greater than 11 or it's greater than 12 terms or less than 12 terms? Well, what you do is, to test it, you substitute in. If you're not sure, get the sum of 3 terms, get the sum of 4 and see what happens. So what's the sum of 4 terms? What's our formula for it? We have sum of 4 terms, where we have n over 2 times 2a plus n minus 1d. Okay, and we have that's 4 over 2 into a was 21, so that's 42, plus n minus 1 is 3, and d is minus 3. Okay, so that's 2 times 42, so that's 42 minus 9 is 33. So the answer is 66. So the sum of 4 terms will give you 66. But the sum of 3 terms will give you less than that. So sum of 3 terms is going to be 3 over 2 into 42 plus 2 by minus 3. So that's 42 minus 6 is 36. Divided by 2, 18 by 3 is 54. S of 3 is 54. Okay, so that shows you that the sum of terms up to 3 is less than 65, but anything over that is greater than 65. So you don't want anything over that. You do the same for S of 11 and S of 12. You probably find that S of 11 is greater than 65 and S of 12 is less than 65. And they're the ones you want. So S of 13 will give you some S of 14. So anything over 12 will give you less than 65. So if you're not sure when you come to this point here, substitute them in very quickly and see. That's how you can verify them. Okay? So that's the end of my presentation. All, thank you for your attention. I just want to also bring your attention to these maths extra books. Not sure if you're familiar with them or not. You can get them free online using this code. They're not expensive to buy, maybe under 10 euros. but they're written very well by an ex secondary school teacher or examiner, I think. And he writes the book specifically to target exam technique, and he cuts through a lot of the preliminary texts that you'd find in your textbooks explaining the background to topics, whereas in this he makes the assumption that you've already worked on the topic, and he gives you challenging questions and examples. And I think it's an excellent book. It's an excellent set of books, very good in preparation for your Lebenscert.
I'd like to say thank you very much, Suzanne, for a great presentation.
Welcome.
All that's left for me to do is remind you that next week we will have the statistics tutorial. So we will hope to see you there. Bye for now.